So theme for waves, lights, and optics. So like I said, these three things are related to one another in the way that light is a type of wave. So because light is a type of wave, then we study waves first. And optics is basically how we can use things such as glass and other things to basically control or manipulate light and how light moves and those kinds of things. So all of these are things that uh, related to one another. So concepts and phenomena of waves, light, and optics have many applications in our lives. I think that's very obvious, especially light. I think we all need light. We all need to have light, but also waves because, like it says here, propagation of waves, property of light and electromagnetic waves. This knowledge is applied in wireless communication, home appliances, medicine, industry, and others. So even right now, uh, just us having this class, uh, the, we are already using these concepts. You know, this internet, or rather, my Wi-Fi connection is using a certain type of wave, and those waves are being sent down cables, and then if you're using your phone, then it's another type of wave being sent to your phone, and you are able to see this class through the internet or other types of wireless communication. Cell phones also use types of electromagnetic waves. Home appliances, so things like microwaves, um, of course, electronic devices, remote controls. Okay, medicine, we can use waves to treat diseases. Uh, Radiation, we have, of course, in use of industries and other things. Okay, so chapter 5 will be all about waves. Now, when I say waves, I'm not just talking about ocean waves, right? Usually, when we say waves, I think that's the first thing that comes to most of us. You know, waves in the ocean. Now, waves in the ocean. Yes, they are a type of wave, but uh, water isn't the only kind of thing that can produce waves, right? So, what is a wave? Basically, the first thing we need to know: what are the properties of waves? What are the phenomena of waves? How do the phenomena of waves affect our lives? Very important. What are the type of electromagnetic waves in the electromagnetic spectrum? So probably the type of wave that most of us use the most often is electromagnetic waves, right? That's the type of wave that is being used in wireless communication, internet, remote controls, and all those kinds of things. However, there are also different types of electromagnetic waves, and these different types of electromagnetic waves, we put them on what we call the electromagnetic spectrum. So we have one type of wave here and another type of wave here and different types of waves. How do we categorize these different types of waves will also be something that we will discuss in the coming chapters. So chapter 5, as you can see, actually has quite a lot of topics, 7 topics overall. We'll only be going into one today, and we'll see. Probably we'll do one today, and then the next class we might be able to cover 2 or 3, depending on how long the material is and how easy it is to understand. But today we'll be dealing with fundamentals of waves. So what are waves? The basic of what a wave is. And then we'll talk about damping and resonance. Okay, how can we make waves stronger or weaker, basically? Reflection, refraction, and diffraction. Interference of waves. How waves can interact and interfere or cancel out one another. And finally, we'll talk about electromagnetic waves and how we use them. So fundamentals of waves, the basics basically of waves. So when you read the word waves, what example of waves do you think of? So I think I mentioned this earlier. Probably the most common type of wave that we would think of is the, water wave, waves in the ocean, right? We can see some example of waves here. So photograph number 1 objects falling on the surface of water produce water waves. I think that's the most common one. Photograph 5.2, striking a leather membrane covered drum or a kompang produces sound waves. So that's another type of wave that we actually come across every single day. So sound is also a type of wave. Okay, so what is a wave and how is it produced? So basically, waves can be produced by an oscillating or a vibrating system. Basically, what it's saying is, gelombang in Malay, what it's basically saying is gelombang ini dihasilkan oleh getaran. Right? That's not a surprise. We learned already before that, for example, sound is produced by vibrations. So waves as a whole are actually being produced by vibrations or oscillation or oscillating. So for example, the oscillating of an iron bulb on the water produces water waves. So if you have an iron bulb and the iron bulb moves up and down on the water, that movement causes waves in the water. Or the vibration of a tuning fork. If you take an object and you make a noise with it, the vibrations of the object produces sound waves. So what is an oscillation and vibration? So the definition is oscillation and vibrations are repetitive motions about an equilibrium position in a closed path. So let's simplify this sentence because it's a little bit it's very scientific. So let's put it in simple terms. Oscillation and vibrations are repetitive motions. So repetitive means this motion keeps on repeating. So it doesn't just stop. So for example, when something vibrates, it keeps doing the same movement over and over without stopping, continuously. That is what causes the waves. Okay, about an equilibrium position. So when I say an equilibrium position, we know what equilibrium is. Equilibrium is a state of basically when something is in balance, right? Or when something is stable. So even though something is moving, it will always come back if something's vibrating, let's say a guitar string. When a guitar string is moving, it always comes back to that equilibrium position in the middle, right? That's how a guitar works. Or any other instrument works. So when we say oscillation and vibration, there is an equilibrium position. So whatever object is vibrating or oscillating, it always tends to come back to that equilibrium position. Another example, if we look at waves in the water. You can see the waves in the water, but eventually the surface of the water returns to being flat, right? It wants to go back to that middle position or that equilibrium position. And the last thing is this one, a closed path. So in other words, when we talk about waves, there is something that stops the object from moving around. Again, coming back to that earlier example, if we have a guitar string, right? The guitar string can vibrate, but because the guitar string is attached to the guitar on two ends, the string cannot actually move. What I mean is the string is not free to go about. It can only stay in that position and basically vibrate there. Same thing with the water, right? It's in a pond or something. It might be able to move a bit, but it's a closed path. It's contained in a certain area. So those are basically the three things, the three main things. So repetitive motions, equilibrium position in a closed path. So these three things are what causes a wave to occur. So through activity 5.2, so if you have your textbooks, you can see this activity. We can conclude that waves are produced when a medium, it can be anything. It could be water, it could be the string of a guitar, it could be air, or it could even be atoms or electromagnetic waves. When this medium vibrates at a fixed position. Now here's the very interesting thing. Propagation of the waves, propagation means movement of the waves, transfers energy from one place to another without transferring the matter of the medium. That is a very important thing. Do I have another picture here? Okay, yeah. So it's a very important thing. So we have this picture here that shows what is basically a spring. And this spring shows everything that I was just talking about, or we were just mentioned about. So first of all, you can see on the left side of the spring, one person is basically shaking the string left and right. Now, because the other end of the spring is being held down, we can say that this spring is in a closed path, right? It doesn't just move around wherever it wants to go. And of course, we have the repetitive motion, and we have the equilibrium position. So the spring has an equilibrium position. The spring has, naturally, if you don't shake the spring wants to be straight. Excuse me. The spring wants to be straight. But because you're giving energy, or you're basically vibrating it or oscillating it, it moves in this wave position. Now, the interesting thing, you notice that while this hand on end A is moving, right? It's moving. You're giving energy, right? The energy from end A goes to end B. So you're sending energy from one side to the other without actually moving the spring. What I mean is, only the energy goes from one end to the other. The spring itself, even though it's vibrating, it's not like the spring, the metal of the spring starts to move from one end to the other. So that's a very interesting and very important concept in the idea of waves. You can move the energy without having to move the medium with it. This is how wireless communication is possible. You can send energy basically through electromagnetic waves without having to send a wire along with it, without having to send it along. Same thing with water waves. You can transfer energy from one end of a body of water to the other, but you don't have to move all of the water along. And so that's another huge, I could say a huge characteristic or a huge phenomena that happens when we talk about waves, is that the energy transfers, but the matter, okay, dia punya jisim ataupun jirim, that does not move. Okay, the medium still is there. Exactly. So movement of waves from end A to end B transfer energy from A to B, like I was just saying. And the ribbon only vibrates about in a fixed position. So the ribbon, so if you were to put a ribbon on a spring, you notice that the ribbon will not move. Only the energy will move along, but the ribbon does not move, meaning to say the matter is not being moved, only the energy. Alright, so what this means is that if we know how to control the different types of waves, then we have a way of transferring energy without transferring the medium. That's how we get things such as wireless communication, wireless charging. You can transfer the electric energy without having to actually have a wire. You can have all kinds of, basically anything wireless, it has to use some type of wave, because it's the only way you can send the energy without using or having a medium to move. Okay? Now, there are different types of waves. And each of the different types of waves have different properties. There are different ways we can classify waves. There are different ways we can say, we can tell the difference between different types of waves. So for example, figure 5.5 shows the shape of the slinky spring at 5 consecutive instances. So when it says 5 consecutive instances, you can imagine if you were to take a camera, right? And you do what's known as, if you know what a burst shot is, or basically when you take a camera and you just hold down the button and the camera just keeps shooting pictures, click, 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 click. So if you were to take a spring and if you were to make a wave, and then you take a camera and just let it keep snapping pictures, then what you would see is something like in this picture. You would see that the wave would slowly move across in one direction. Now, when you look at the wave, an important thing or important factor that you need to look at is the shape of the wave. What kind of shape does this wave have? So this shape, we call this the wave profile. Okay. Now, there are two types of wave profiles. There are different types of wave profile that we can study or we can look at. So waves can be classified from the aspect of propagation. So one way is how do I say this? I'm trying to think of a way to make it as simple as possible. So there are several ways for us to look at this. The first is, what is the direction? The wave profile in figure 5.4 propagates with time along the direction of the propagation of the wave. So in this kind of wave, what we see is that over time, as time passes by, the wave moves from one side to the other. Alright, so when you have a wave that moves from one side to the other, then this wave is what we call a progressive wave. It progresses from one side to the other. You can literally see the wave moving from one side to the other. Now, the other type of wave, well, we'll talk about that later. So what we usually see is this kind of wave. Water, you can see the water ripples start from the middle and move towards the outside. Alright, so progressive waves can move in two different ways. I'll come back to this later. Now, the other type of propagation, or the other type of way that a wave can move is, instead of a progressive wave, we can also have something that's known as a stationary wave. So a stationary wave is different in the sense that it does not move left to right, but rather it only moves up and down. So for example, figure 5.6 shows a wave profile at 5 consecutive instances of a guitar string that is being plucked. So if you take a guitar string, you pluck it, and then you do the same thing, take a camera and just keep on clicking with the camera to let it take 100 pictures or so. You don't see the waves going from left to right on the guitar string, but you see the waves of the guitar just going up and down. So that is what we call a stationary wave. Okay, so a stationary wave is a wave where the profile of the wave does not propagate, or it doesn't move over time, or it does not spread, basically. So please get the difference in your head. We have the progressive wave, where the wave starts from the beginning and it moves to the other end. You can see the waves moving along, just like that. If you took a camera, you can see the movement. And the other type is stationary waves, where the waves are actually just going up and down, but they're not actually moving along the path. It does not propagate over time. Now, back to the progressive waves. Now, when we say progressive waves, there are still more differences that we can study. So progressive waves, like we said, it moves a long time or propagates a long time. However, there are two different ways that these progressive waves can move along a straight line, or along a path. I shouldn't say straight line. Okay, it can propagate through a medium either as transverse waves or longitudinal waves. So even for waves that move, there are different ways that it can do it. Alright, so you can see that there are different types. We'll go into this into more detail a little bit after this, but basically the most common one is this one here at the bottom, where we see the waves go up and down. But there are also types of waves where we're actually compressing and expanding. So I'll show you this. I'll show you more of that later. Actually, if you saw the video earlier, that video actually does show a little bit of how this uh, transverse and longitudinal waves work. Okay, so we have progressive waves that move, that propagate, and we have two types. And we have stationary waves that are just stationary and just goes up and down. All right, so waves can also be classified. So another way we can classify a wave is whether it's a mechanical wave or an electromagnetic wave. So the difference is that so the difference between a mechanical wave and a electromagnetic wave is this. So the first one is a mechanical wave requires a medium. It could be water, it could be air, some sort of gas, it could be a solid. The important thing is that it has to have some sort of medium. Whereas an electromagnetic wave does not require a medium. So basically any type of wireless connection is going to be using an electromagnetic wave. Okay, for a mechanical wave, it's made out of vibrating particles of a medium. So for example, a sound wave is made up of vibrating air. A water wave is made up of vibrating or oscillating water. Right? A seismic wave is the earth vibrating in a wave formation. So these are all examples of mechanical waves: water waves, sound waves, and seismic waves. Now, an electromagnetic wave is not made up of vibrating particles, but is made up of oscillating electric and magnetic fields. So what's vibrating is the electric field or the magnetic field, perpendicular with one another. And so because magnetic fields and electric fields are oscillating and vibrating, you create an electromagnetic wave. So for example, radio waves, light waves, and gamma rays. So these are all different types of electromagnetic waves. All right, so let's go back to. So these are the types of the different types of waves that we talk about. All right, now let's come back to what we were talking about earlier. So there are two types of progressive waves. We have transverse waves and longitudinal waves. So what are the similarities and what are the differences between these two? So in a transverse wave, so for most of us, we would consider the transverse wave as more, how to say, this is what we usually think of when we say waves, transverse waves. So particles in the medium vibrate in the direction perpendicular. So perpendicular meaning to say 90 degrees to the direction of propagation of the wave. So what does that mean? If you look at this spring, the wave is going from left to right. Correct? So the wave is moving from left to right, but the spring is vibrating up and down. Right? So this is what we call a transverse wave. The spring is vibrating one up and down, but the wave is moving left to right. So perpendicular to each other. So these kinds of waves are made out of consecutive crests and troughs. Meaning to say, when I say crest, crest meaning to say the top or the peak of the wave, and a trough is the bottom or the valleys in the lowest part of the wave. So the wave goes up and down. So the top part you call it a crest, and the bottom part you call it a trough. So some examples of transverse waves are radio waves, light waves, and water waves. So water waves, you know, they go up and down like that. We see that all the time. Now the other one that is not so obvious and a little bit less, not as obvious, is what we call a longitudinal wave. So particles of the medium vibrate in the direction parallel to the direction of the propagation of the wave. So meaning to say, the wave moves left to right. The vibration is also left to right. So it's the opposite of what's happening here. In here, the wave moves from left to right, but the medium vibrates up and down. Whereas in a longitudinal wave, it moves left to right, and the vibration is also happening left to right. So it's a little bit hard to understand with just a picture. So I'm gonna come back to that video that we were watching earlier, and I want to show it to you again because it's much easier for you to understand when you see it in a video or in a picture. So longitudinal waves. So this was the video that we were just actually watching just a little bit earlier. Let me just share. All right, here we go. All right, so this is an example of what we call a longitudinal wave. So if you look at it, the vibration doesn't actually happen up and down, but it actually happens left to right. Okay, I think that's enough. I think that's enough to give you an idea on uh, how exactly these types of waves work. All right. So when we have these different types of waves, just like it was saying in a video we were just watching, you have areas where the medium is compressed, like down here, and you have areas where the medium is stretched out. So we call these areas compression and rarefactions. Rarefaction just means it's stretched out. So there are parts of where this energy causes the spring to be compressed. There are parts where the energy causes the spring to be stretched out basically in a different form. So in both cases, the wave travels from left to right, but it's just difference of whether the medium is moving up and down like this, or it's also moving left to right like this. So longitudinal wave is a sound wave. One type is sound waves. There are also other types that happens. All right. Characteristics of waves. All right. So finally, we get to a part that this part is what makes waves different. Characteristics of wave. What are the differences between different types of waves? How is one type of wave different from another? And by knowing that, how can we use these waves to transfer information or such things? So figure 5.12 shows the profile of a water wave in a pond. What changes can you observe as the wave propagates across the water? So if you look at this wave, you see that it starts from one side of the pond and the waves end up on the other side of the pond. But you look carefully, as the wave propagates from one side to the other, the wave starts to change. Right? So what changes are happening? What types of changes are happening? If you were to write this down, if you had to write it down in a book, for a scientific study, what kind of changes are happening? Because you cannot just say, "Oh, the wave, it looks different." You have to be specific. So just look at that picture. So specifically what happens are, well, let's just look at a few. What is the difference between this first wave here and this last wave? Well, this last wave here, for one, it's taller. The distance between the throw and the crest is greater than the wave here in the beginning. So here on the left, the crest and the throw here on the left side, the difference is not that big. And then here on the other side, the difference between the crest and the throw starts to get bigger. So that's one. What else? You also notice that the distance or the length of each wave starts to get shorter as you go from left to right. So the waves on the left side are quite long. And on the right side, the wave is much shorter. Okay, what else? The other things. So these are the 5 characteristics that we need to remember. So definition of terms related to waves. So the first one is amplitude, A. So defined as the maximum displacement of a particle from its equilibrium position. Basically, in simple terms, all right, if we have the equilibrium position, how far do we go away from that equilibrium position? So something that has a small amplitude only has a small displacement from its equilibrium position. Something that has a large amplitude will go further away from its equilibrium position. So if we were to compare, for example, in this picture, the wave in the beginning has a very small amplitude, right? Because the distance between the top part and the low part isn't really that big. However, as we get closer and closer, or further and further to the right, you can see that the amplitude starts to get bigger because the distance between the highest part and the lowest part starts to get greater. So that's one. Okay, the other one is the period. So period is the time taken by a particle to make one complete oscillation or by a source to produce one complete cycle of wave. So basically, how long does it take for it to create one wave? So one complete wave is up, down, and then back to equilibrium. That's one wave. So period is how long does it take? How long does it take to go up, down, and back to equilibrium? That's period. Frequency. So frequency is number of complete oscillations made by a particle or number of cycles of wave produced by a source in 1 second. So in 1 second, how many complete waves do you produce? So we use the word hertz to describe it. So something that is 20 hertz, for example, means it only completes 20 cycles, so 20 waves per second. So that's considered quite, if it's a sound wave, that's considered quite low. That's basically the lowest a human can detect. Or an oscillation, it might be very high frequency. It might be 20,000 hertz in 1 second. So frequency is how many waves, how many complete waves you create in a second. Okay. Next one is wavelength, distance between 2 consecutive points in phase. I'll explain what the word in phase. So basically, for example, if you have a complete wave, how long is it from one crest to the other crest? Or how far is it from one throw to the other throw? That's what we call wavelength. And finally, we have wave speed, which is distance traveled per second by wave profile. So how fast this wave is moving from left to right. Now, it's very important for you to know that period and frequency and wavelength, these two tend to be very close related, especially these two, frequency and period. Because if you think about it, period is how long it takes to complete one cycle. One complete cycle. Frequency is how many complete cycles in 1 second. So basically, the shorter the period, meaning to say, the shorter the time it takes to complete one cycle, the higher the frequency. Because shorter period means less time for one cycle, meaning to say it's easier to create more cycles in 1 second. So you end up with a higher frequency. So when you are reading the questions later, these are two things that you can keep in mind. So you can think, okay, if a wave has a very high period, meaning to say it takes a long time to complete one period, then automatically the frequency is going to be lower. Or if the period is very small or very short, then you'll actually end up with a very high frequency because it means that you can complete more in 1 second. All right. And the other ones is wavelength and wave speed. So how fast these waves can travel and how long the waves are. All right. So, sorry. All right. Sorry, I knocked over a cable earlier and had something happen. Okay. So amplitude, point in phase and wavelength of a transverse wave. So when I say a point in phase, like I said just now, I always said, distance between two consecutive points in phase. We mean to say 2 points that are in the same, basically in the same condition. So basically 2 points at a crest. Okay, then we can call this 2 points in the. So all the yellow X's are points in phase, right? They're all in the same state, which is the crest. Okay, all the blue Z's are also in phase because they're basically in the same sort of state, being in the valley. Or all the green Y's are in phase, meaning to say they're all in equilibrium. Right? So you need to know where these points of phase are because you need this to measure the wavelength. All right? So you can, for a transverse wave, you can measure the wavelength by either measuring one crest to another crest, or one throw to another throw, or one equilibrium position to another equilibrium position. Personally, I would use either the crest or valley. That's a little bit, there's less chance for making a mistake. If we use the equilibrium, you might make the mistake of measuring from, look at it. There's Y1, right? You go up and then you go down, right? You cannot measure from when you go up and then you go down. You have to wait it for also going back up. So it has to be moving in the same direction. So you might make a mistake if you're measuring from Y. There's less chance of a mistake if you're using either X or Z. Now this is for a transverse wave. For a longitudinal wave, then you have to measure from the point, the distance between the compression and the rarefaction. So all the points where it is most compressed, so all this purple letter P, are considered in phase, and all these points where it's most stretched out or rarefaction, Q, are also considered in phase. So you can use either one to measure the wavelength. So keep that in mind. Now figure 5.15 shows the profile of a transverse wave at one instant, and after a period T of the wave. In time, T equals T, the wave profile propagates through the same distance as the wavelength there. So what is basically saying, and we will talk about this later, you can use the period and the wavelength to calculate how fast, and you can use these things to calculate things such as how fast the wave is moving, how far the wave is going to move, how much time it's going to take to travel a certain distance. So for example, if you know the period, if you know that it takes a certain amount of time to complete one wave, and you know how far each wave is, then it becomes easy for you to calculate how long it takes to cover a certain distance. So you know, or you can use it to calculate how fast the wave is. So all these things, don't just try to remember this one by one, but also try to think of what are the relationship between these different values. All right. So this formula that we can use to calculate the speed of a wave, right? So speed we know is distance over time, right? So in this case, we are calculating the distance traveled by a wave profile. So speed of a wave equals the wavelength divided by t, or the period. So we can use this formula to calculate how fast a wave moves. So 1 over t times the wavelength. That's how you figure out how fast this wave is traveling. Now you can also use this to calculate the frequency. So frequency is 1 over t. So speed of a wave equals the frequency times the wavelength. Later, and your homework will be to try out these formulas later. So we can also learn to sketch and interpret different types of graphs and different types of waves. So the profile of a transverse wave at a certain distance. So particles along the waves oscillate up and down about the equilibrium position. So two types of graphs can be drawn to show the variation of the displacement of wave particles, which are graph of displacement against time and graph of displacement against distance. So we can draw different types of graphs, and we can use these graphs to interpret and basically learn more about the different types of waves. So displacement against time and displacement against distance. So for example, graph of displacement of against time, it would look something like this. So you have time along along one axis, and the other axis shows the displacement. So you see that over time the displacement goes up and down, and you can see the period. So you can see the time it takes to go from one cycle to another. You can also see the amplitude, and you can also calculate the frequency. So for a displacement against time graph, the information that it gives you is the amplitude being how tall the waves are. It gives you the period, how much time it takes for one wave to happen. And if you know how much time it takes for one wave to happen, you can easily calculate how many waves will happen per second, or the frequency. Okay. Now the other type is sorry, I made a mistake. This is a graph of displacement against distance. This is not sorry. I'm sorry. This is not a time graph. So displacement against time. Now displacement against distance. Now it looks quite similar. Because what you're measuring is the distance. So after 1 cm, or basically after 0.1 cm, what does the wave look like? After 0.2 cm, what does the wave look like? So in a displacement against distance graph, the information that it gives you is the amplitude, and it gives you the wavelength. Because remember, this is displacement over distance. It tells you, okay, from here to here, how many centimeters have you traveled? And so you can understand the wavelength. But it doesn't tell you the amplitude, or it still tells you the amplitude, but it doesn't tell you the period or the frequency. So by using these different types of graphs, we can make different calculations and sort of predict the waves, how far the waves will go, how fast the waves will travel, and such. So in a laboratory, a type of experiment that is done in a lab is what we call a ripple tank. So a ripple tank is basically a water tank made of glass or perspex, something clear, and we have a machine to create the ripple, so a ripple generator, so some sort of machine that makes the wave. We have a digital xenon stroboscope, so it's a type of a scope that looks at the waves and studies and calculates and detects the waves. And of course, we have a mirror and a glass screen and a dipper. So a dipper is something that you dip in the water to create the waves. So there are several types of machines that you can use. This is kind of what it looks like. And this is how it looks like. So you use the machine to create a waves. You can have a plain dipper, which is straight. Or you can use a spherical dipper, which causes circles. And this spherical dipper produces circular waves and planes. So this is just an experiment that is usually done in the lab. You just need to know this because sometimes questions in the exams will ask you to talk about different types of experiments. KBOT questions, paper 3 will have a lot of experiments in them. In fact, for SPM, paper 3 is Amali, which is you have to do the experiment in front of a teacher, and the teacher cannot help you. So you need to know these things. Okay, so this will be our assignment. For how much time do we have? You still have some time. So for the rest of the class, which will be formative practice 5.1, let's just talk a little bit about the questions that we have here. So figure 5.2 shows a graph of displacement against time for a wave. So remember, when you're reading these questions and there's a graph, you have to make sure that you to be careful as to what type of graph it gives you, because a displacement against time and a displacement against distance are two different types of graphs. And the kind of calculations that you can do will be different. Okay. Number 2, compare and contrast progressive and stationary wave. We talked about that earlier. And number 3, a slinky spring moving back and forward. So if it's moving back and forward, what type of wave is it? Okay, mark X at the rarefaction. So where's the rarefaction and where's the compression? And what is the wavelength of the wave? And you can see a picture. It gives you a measurement. So you can use that to calculate that. Okay, so you have about 20 minutes left. Do you have any questions before I let you off to do this work or do this assignment? Any questions about waves, or is there anything that you're still not 100% clear about? Because we still have time for some extra explanations. Okay, so none from Emmanuel. How about the rest of you? Let me just stop the recording first.